Hello, this is Math 102 Calculus 2 Final Exam Review. Number 1. Approximate each of the following integrals by both trapezoidal rule and Simpson's rule with n equals to 6. Compute as much as possible without using a calculator. Alright, so we have the Simpson's rule and trapezoidal rule. Let's write down the formulas first. The trapezoidal rule is you have delta of x over 2, and you start from f of x naught and twice of f of x1, and then plus twice of f of x2, and so on until you reach the last one, which is f of xn. And I hope you still remember what x naught and xn is. Basically what you're trying to do is, if you're given an interval a to b, you're trying to divide this into n equal intervals. And since you have n equal intervals, the size of one interval is called delta of x, which is b minus a over the number of intervals you have. So b minus a gives you the length of the interval, and if you divide by n, you get the size of one interval. And then x naught would be the very beginning point, the left end point of the first interval, which is a. And then to get to the next point, you just add delta x, and x2 would be a plus 2 delta x, and you just keep adding just as many delta x's as you need, starting from a. So that's what these symbols mean: delta x, x naught, x1, and all that. For Simpson's rule, you have a similar looking formula, but the difference is that instead of having 2, 2, 2, 2 all the way, it should be 4, 2, 4, 2. And 4, 2, 4, 2 should be repeated until you get to the last one. It should end at 4, and then you get xn. Now, for this to actually work, in order to have the 4 right before f, it turns out that you need even number of intervals, so that if n is an even number, the entire thing is an odd number, and somehow it works out that you start with 4 and you end with 4 right after the beginning and right before the end. Okay, now let's try to apply these formula for the sine of x. First, you have to compute delta of x, which is 2 pi minus pi over 6. Notice that pi to 2 pi is the interval that you're integrating, and n is given as 6. So I'm using the formula delta of x equals to b minus a over n. And whenever you have any kind of rules, you probably know that there are more than this. There's a left sum, right sum, the midpoint formula, and all these other ones. You should have them memorized, and whatever formula that you use, you should always start by computing the delta x, because delta x gives you the length of one interval. And it's also the step size for figuring out these points. If you know one point where you begin, then the next point would be this step size added. Okay, so what do we have here? 2 pi minus pi is pi, and you divide by 6, so that's your delta x, which tells you that since you're starting with pi, x1 would be pi plus pi over 6, which is pi over 6 plus pi plus pi over 6, which is 7 pi over 6. x2 would be 7 pi over 6, and add pi over 6 yet again, and that would be 8 pi over 6, and you can reduce this as 4 pi over 3. x3 is 4 pi over 3 plus pi over 6. You keep adding pi over 6 because that's the step size. And then 9 pi over 6 is what you get, which is 3 pi over 2. x4 is 3 pi over 2. Add the step size. Let's see. This is 9 over 6. So 9 plus 1 gives you 10 pi over 6, which is 5 pi over 3. Now, when do you stop? You stop when you reach the right end point, which is 2 pi. Since we're still under 2 pi, we should carry on. And x5 is 5 pi over 3 plus pi over 6. 5 pi over 3 is 10 pi over 6. So when you add pi over 6, it's 11 pi over 6. And x6 is 11 pi over 6 plus pi over 6. So you get 12 pi over 6, and that is equal to 2 pi. And you reach the right end point, which is 2 pi. So that's good. Okay, and make sure that you reach that right end point when your subscript reaches the number n. N is given as 6, right? So when x6 is 2 pi, that means you didn't make any mistake in finding all these numbers. Okay, now let's put everything into the trapezoidal rule. T, therefore, is pi over 6, that's the size of delta x, divided by 2. And then you have to evaluate the sign at pi. That's where you start. Sine pi plus twice. Notice that in the beginning and the end it's 1, but everything in between you have to multiply by 2. So sine pi, and then 2 times sine of 7 pi over 6 plus 2 times sine 4 pi over 3 plus 2 times sine 3 pi over 2 plus 2 times sine of 5 pi over 3 plus 2 times sine of 11 pi over 6, and then finally sine of 2 pi. Okay, so it's pi over 12. Sine of pi is 0. This is negative 1/2, so it will be 0 plus 2 times negative 1/2. This is plus 2 times negative radical 3 over 2 plus 2 times negative 1 plus 2 times negative radical 3 over 2 plus 2 times negative 1/2, and then plus 0. Okay, I don't have any room, so let me raise it a little bit. I'll raise here. And let me continue up here. Okay, so we have, therefore, pi over 12. I see negative 1, negative 2, negative 1. So if you add all the integers, you get negative 4. Also, I have negative radical 3 and another negative radical 3, so I have negative 2 radical 3. And since everything in here, 4 and 2 are both divisible by 2, I guess I should reduce this. Also pull the negative out, so I think I have pi over 6 times 2 plus radical 3. That will be the trapezoidal one. Okay, now what about the Simpsons? Simpsons would be pi over 6 divided by 3 this time. But then instead of having 1, 2, 2, 2, 2 all the way 0, these will be 4. This will be 4, and that will be 4. So if I just, since I'm going to be using the same values, but just the different coefficients, let me just copy what I have down here, but then change this to 4, negative 1/2, plus 2, negative radical 3 over 2, plus plus 4 times negative 1 plus 2 times negative radical 3 over 2 plus 4 times negative 1/2 and then plus 0. Okay, if I do that, this will be pi over 18, whereas this is negative 2, negative 4, negative 2, so it will be negative 8 overall. And again, this will be minus 2 radical 3. Then, again, if you simplify, minus pi over 9, be negative pi over 9, times positive 4 plus radical 3. Okay. Now, which one of these are better approximations? Simpson's rule usually gives you the better approximation, except for very rare cases. So when it comes to using this integral for approximating area and stuff, usually engineers would use the Simpson's rule. Let's move on to the second one. This one we have delta of x. Always start with delta of x. So we're working on this second one here. Delta of x is b minus a, 2 minus 1, divided by 6, because n is given as 6, so that's 1 over 6. And then your left endpoint, the very beginning x0 is 1, because that's where you start. Then x1 would be 1 plus 1 over 6, which is 6 over 6 plus 1 over 6, which is 7 over 6. x2 would be 8 over 6. x3 would be 9 over 6. x4 would be 10 over 6. Because you keep adding 1 over 6, right? x5 would be 11 over 6. x6 is 12 over 6. But then these you can reduce. This you can reduce. This you can reduce. This one you can't. This reduces is 4/3. This is 3/2. 5/3. And this is 2. And as you can see, x6 reaches the right endpoint, so everything's good. Now, t is 1 over 6, that's your delta x, divided by 2, square root of 1 plus 1 cubed, because that's your very first x0, twice of square root of 1 plus 7 over 6 cubed, and then twice of 1 plus 4/3 cubed, plus 2 times square root of 1 plus 3 over 2 cubed, plus 2 times square root of 1 plus 5 over 3 cubed, plus 2 times square root of 1 plus 11 over 6 cubed. And then, since x6 is the last one, the first and the last you don't multiply by 2. Only the ones in between you multiply by 2. So this last one is 1 plus 2 cubed. Okay. Now I will not tell you how to simplify this, because after this is pretty straightforward. Sometimes the test might ask you to use calculator to compute this, and sometimes it might not allow you, so you'll have to compute everything. Now, one more thing I want to say is that this integral, square root of 1 plus x cubed, cannot be integrated by U-substitution or anything that you know. These are what we call elliptic integrals, so when you want to define the antiderivative of this, you end up using some strange functions called elliptic functions, which you never have learned before. So for engineers, if this type of integral ever comes up, sometimes rather than using all these weird elliptic functions, it's better to just have an approximation of that by using these methods. Of course, when you implement this, you would usually use a computer, so n would be a very large number, so you have like 1,000, and you rather than the trapezoidal, you'll probably write a program that would calculate this using Simpsons. Okay, in the same way, the Simpsons would be 1/6 divided by 3, and then it's exactly the same thing, except that there are 4 before the first one, and the pattern is 4 2 4 2 4 2. It just repeats. Okay. Oh, why did I put 7/6? This is 4/3, and this is 3/2. Okay, and then 2 times 1 plus 5/3 cubed plus 4 times square root of 1 plus 11/6 cubed, and then finally you have square root of 1 plus 2 cubed. Okay. A particle moving on x-axis is initially at x equals to 2 and is accelerating by a of t, 5 minus 6t. If the initial velocity is v0 equals to 2, find the following. Velocity at time t equals to 1. Velocity at time t equals to 1 would be, first you have to find what v of t is, and, well, since if you differentiate the velocity, rate of change of the velocity is acceleration, that means if you integrate the acceleration, you're going to get the velocity. Which means you have 5 minus 6t dt, and that's equal to 5t minus 3t squared, and then plus c. There's an ambiguity here because you need just one extra information. You need the initial speed or the velocity at other times. Usually the initial velocity is what you're given, but that would determine the c. So v of 0 is 2. That's what it says here, which means that when you plug in 0, you get 5 times 0 minus 3 times 0 squared plus c. That's equal to 2, and therefore c is 2. So what does that mean? V of t would now be 5t minus 3t squared plus 2. And therefore you can now plug in 1 to find the value of the velocity at t equals to 1, which gives you 5 minus 3 plus 2, and that's 4. So 4 is the answer to A. For B, to find the position function, you would integrate the velocity. Integrating the velocity will give you the position function. 5t minus 3t squared plus 2. So that's 5 over t squared minus t cubed plus 2t. Again, you get this c. And the initial position is at x equals to 2. Therefore, you should say, since this is your st, and since if you plug in 0, you get 5 over 2 0 squared minus 0 cubed, 2 times 0 plus c. This is what you get for s of 0, but s of 0 should be 2 because that's where it begins. So again, you get c equals to 2, and therefore the final answer for that would be s of t is equals to 5 over 2t squared minus t cubed plus 2t plus 2. Okay, now what's the total distance traveled from t equal to 0 to t equals to 3? Well, if the question was what is the displacement from t equals to 0 to t equals to 3, then all you care is where was the initial position. Well, that was 2 that we know. Where's the position at time t equals to 3, and to get that you would plug in 3 here to get it. And you just take just measure the distance between 2 points, that would be it. But when you're being asked distance traveled, that's a different story, because it could be that something would move this way, and then it would come back. Yeah. If the velocity changes from positive to negative, then this can certainly happen. If that happens, then the distance traveled is not just the distance between the initial point and the final point, because this would be much less than the actual distance traveled. So what you need to do is you need to know when it turned back, and you actually have to calculate the distance between the initial and the point when it was turning, and also the distance between the final and the point it turned, and then add the two. That will be how we handle this. Now, to much complicate the matters, it could be that it went back and forth several times and came to the final position. I'm drawing this as if it's a two-dimensional thing, but it's really one-dimensional. Let's say on a straight line it went here and then came back and then went there and then came back. Then you would have many turning points. In that case, you have to consider all of them. So you'll have to draw this picture and figure out what to do. Okay, now let's see. When does this hit 0? Well, if you look, this is negative 3t squared plus 5t plus 2 equal to 0. So if you multiply by negative, it's 3t squared minus 5t minus 2 equal to 0. And this factors as t plus 1 and 3t minus 2. I'm not so sure. Let's see. 3. No. I see. So this should have been negative 2, and this should be plus 1. Okay, so negative 6 plus 1 does give you that. So this thing factors as t minus 2, 3t plus 1, where it has two solutions, right? T is either 2 or negative 1/3, but negative time doesn't exist, so you just have to use t equals to 2. So we know that at t equals to 2, direction changes. So in other words, it's a turning point. It's this point. This happens at t equals to 2. Now, you could have found these two values, t equals to 2 and negative 1/3, by using quadratic formula. Okay, now that we know that at t equals to 2, the direction changes, what do? We have to figure out the position at s of 2. And we also need to know the position at s equals to 3. Alright, so s equals to 2. 5 over 2 times 2 squared minus 2 cubed plus 2 times 2 plus 2 for 10 minus 8 plus 4 plus 2. So that's 8. Okay, so 8 is the position at time 2. What about 3? S of 3 is 3 squared is 9, 9 times 5 is 45. 3 cubed is 27. 3 times 2 is 6. 6 plus 2 is 8. So over 2 we have 45 minus 54 plus 16. 16 plus 45 minus 54 is negative 9. And then you have plus 16, so it's 7 over 2. Okay, now I need more room somewhere. Let me try to compute over here for this one. This one now would require the distance between 8 minus 7 over 2, which is 16 minus 9 over 2. So that's the distance between time 2 to 3. And also, the final position 8, and the distance between the initial position would be 8 minus 2, which is 6. And you have to add these two, which is 12 plus 9, 21 over 2. So 21 over 2 would be the actual answer to this part C. Okay, so what is average speed? Average speed is the total distance traveled divided by total time. Because we just figured out that 21 over 2 is the total distance, and the total time from 0 to 3 would be, I should have said average speed from t equal to 0 and t equals to 3, so forgive me for that. What is the average speed from t equal to 0 to t equal to 3? We know that the total distance traveled is 21 over 2, and the total time it took is 3, so you end up with 7 over 2. What about the average velocity? Well, the average velocity is a displacement, so it's different. Displacement is just trying to figure out the difference between the final position minus initial position. So displacement is final position minus initial, and you divide by time, that's what it's looking for. We know that the final position is 7 over 2, initial position is 2, and the time is 3. So we have that's 4 over 2, so 3 over 2 divided by 3, so 1/2 would be the average velocity. Now here we have a graph of a function, and we're going to assume that these are made by straight lines. And the first question says, compute the integral from 2 to 6 of this function. So that means I want the integral from this 2 until 6 here. And you have to understand that the meaning of the integral is the net area. Net area. When you say net value, that means it's like a total, but it's like the sum. You have to figure out what's the income and what's the outcome, and then you do subtract. You have to subtract income from outcome. So net of something usually means that you add something, but you have to figure out the signs. Sometimes it should be subtracted rather than added. Now, in the integration case, what it means is that it's the area, but when it's under the x-axis, you consider the area to be negative. So all these here are considered negatives, but over here, this one is considered positive because it's over the x-axis. So what's the net area? Well, think of it like this. You first have this this square plus another square here, and then another square here. Actually, that's not a square, that's a triangle, right? Triangle. And then there's another triangle, but I said it's a signed area, so these are negatives, whereas this is positive. Now I know the area of a rectangle, a square, it's 1 by 1, so I multiply 1 times 1, so it's -1 here, -1 there. What about this? This is half of a triangle, so it must be -1. A triangle is half a square, so it must be half of the 1, so it's -1/2. -1/2 is the area. Or you can just do base times height, right? Base times height times 1/2 gives you the area, plus 1/2, and these two cancel, and this one gives you -2. So that's the answer. Now, what about 2 to 6 absolute value of f of x? Well, when you take the absolute value, the effect on the graph is that anything that's under is flipped over, and you end up with a new graph, which is like this. Okay, and therefore, what used to be below the x-axis now becomes over the x-axis. So when you integrate the absolute value of a function, you end up with just the total area where you consider all the area as positive. So this time it would be like you're adding all the areas that you mentioned before, but this time you'll be adding them. So this is 1 plus 1 plus 1/2 plus 1/2, which gives you 3. Now part C has to do with figuring out the integrals by linearity of an integral. What is linearity? Linearity means when you have addition or subtraction, you can split the integral this way. And then furthermore, when you have any constant multiple, you can pull it outside. So it's 2 times 2 to 6 f of x dx. And this one you can just, you could draw y equals to 3 and then figure out the area that way. Or you can just use the fundamental theorem of calculus, which is if you integrate 3, it's 3x. And you have to put 6 and 2. Either way, if you know graphs well, you can quickly just see that this is 12 just by mentally drawing the graph. That would be very good. But if you can't, just compute this. When you compute it like this, be sure to put a parenthesis here so that you don't get confused with the negative signs. Always when you use the fundamental theorem of calculus, the negative sign is an issue. Many people make mistakes in the negative sign. Alright, 2 times the integral of this, which we figured out as -2 there, so I'm going to use that value. And then when you plug in 6 here, that's 18. 2 in here, 2 times 3 is 6. So you end up with -4 minus 12, which is -16. So -16 would be the answer to this. This would be 3. Solve the following integrals. Now, you're faced with this integral here where it looks very hard. First of all, this is multiplication, so you can't integrate these separately. That's not allowed. On the other hand, since this is the 5th power, if you expand this, multiply this by itself 5 times, that's a lot of work. It will take forever to do the integral that way. So then the next thing that you observe is, well, if you differentiate this, that's like 4x plus 2 plus 0, if you differentiate that. And this happens to be twice of 2x plus 1, which is just a multiple of this. Oh, so you see that when you do a U-substitution with this, this will end up being absorbed when you calculate the d of u. If you take this as u, then this will go away. I tend to call this the artifact of the chain rule, because really what U-substitution is doing is because it's trying to undo the chain rule, and when you think about what function you had to differentiate to get to this, you realize that this one really wasn't there before, but it was made here because of the artifact of the chain rule, because the chain rule made it here. Okay, so anyways, what I'm trying to say is, let's erase everything. What I'm trying to say is that you just want to take the U-substitution with 2x squared plus 2x plus 3, so that d of u is the derivative of this, which is 4x plus 2 dx. And you should always solve for dx. So divide by this, so you get 1 over 4x plus 2 du. And then you can just put everything in there, hope that this 1 plus 2x goes away. It will go away. Now, but when it's a definite integral, there's one more thing that you have to do. You have to figure out the value of u when x becomes -2 and when x becomes -1. Okay, x equals to -2. Let's see. What does that mean for the value of u? U becomes 2 times -2 squared plus 2 times -2 plus 3, which is 8 minus 4 plus 3, which is 7. And x equals to -1 would make u equals to 2 times -1 squared plus 2 times -1 plus 3. And that's 2 minus 2 plus 3, which is 3. That means this integral is now equal to 1 plus 2x. I don't know what to do with that. I know that 2x squared plus 2x plus 3, that is u. So I have u to the 5th power. And then your dx is now 1 over 4x plus 2 du. And since you have du here, the values you put here and there cannot be -2 and -1 because here you have dx, so these are values of x. You're not allowed to put the values of x here when it's du. You have to put the value of u. That's why we did all this work, okay? So that's one thing that a lot of people overlook. You should always do this work. Okay, now you can't integrate this now because you still have some x's there. If you still have x's, then you're not permitted to do any more integration. You have to make sure that you take care of this integral so that no more x's are seen. And only after that you may integrate. So 4x plus 2, 1 plus 2x. What's the relationship? Well, 4x plus 2 is twice of 2x plus 1, which is twice of 1 plus 2x. So you can rewrite this as 1 plus 2x times u to the 5th power, 1 over 2 times 1 plus 2x du, and then 1 plus 2x and 1 plus 2x cancels away, and now you have 1/2 times u to the 5th power du, integral from 7 to 3, which can be integrated using the power rule because you add 1 to the exponent and you put the reciprocal in front. That's called the power rule. When you integrate a monomial, x to some power, then you use the power rule. And then you have to plug in 7 and 3. Let's see. 1/2 times 1/6 is 1 over 12. And you get 3 to the 6th power minus 7 to the 6th power. Well, that's a huge number, so I'll leave up to you to figure out what this really is exactly. Okay, next. Here we have a polynomial times e to the x, and I know that x squared plus 1 is not something like an artifact of the chain rule like what we had before, because it's just simply x. I mean, if I had something like, say, x cubed plus x, and then I had x squared plus 1, then, oh no, I should have something like 1/3 here. Okay, if I had something like this and integrated against this, then because the derivative of this is equal to this, I would know that the way to integrate would be to take this as u, which is the inside function, and naturally when you differentiate this, this will be created, so this will be gone when you do the u-substitution. However, you just simply have e to the x in this case, so this is not done using u-substitution. What else do you do then? When you have a product, again, another thing is that when you have a product, you're not allowed to integrate them separately, so you need to do something, and that something is what we call integration by parts. So how do you do integration by parts? Well, you have to choose, well, the integration by parts formula is integration of u dv is equal to uv minus v du. So you have to choose what u is to be equal to and what dv is to be equal to. Now when you choose u and dv, usually the way you choose it is what you call the Lie, and L is for logs, I is for inverse trigs, A is for algebraic functions, so like something like polynomials, T is for trig function, E is exponential function. And since x squared plus 1 is an algebraic function here, and e to the x is an exponential function, Lee 8 says that you should let u to be x squared plus 1 and e to the x to be v. So we put u as x squared plus 1 and dv as e to the x, and the reason you put dv is because it has to include your d, the variable that you're integrating with. I think you call this the integration form. Alright, so now we have this, and since you need to know what du is and what v is for the right side to be completed, you have to figure out du and also v. Okay, what's du? Du would be the derivative, which is 2x and then dx, and this would be the antiderivative, which is e to the x. Integrating e to the x gives you e to the x. And now you're almost done, because now you have x squared plus 1 e to the x dx equals to uv, so these terms multiplied, x squared plus 1 e to the x minus integral of v du, so it's this times this, so it's e to the x times 2x dx, and then since this is it's a definite integral 0 to 4, all of these should have 0 to 4 and 0 to 4 there. Okay, well, what do we have here? We still have a product of two things, which still is not in any way the U-substitution form. So that means you have to do integration by parts again, which is quite annoying. There is a faster way to do all this process, which is called tabular integration. If you have the time to learn it, it would be nice if you can learn it. You can find one in my channel. If you search for tabular integration in my channel, you'll be able to find it. That's much faster. Okay, so when you plug in 4, you have 4 squared is 16, 16 plus 1 is 17, 17 times e to the 4 is what you get. When you plug in 0, you get 1, and e to the 0 is 1, so you get minus 1. So that's what you get from this one. And then this here, you still have to do integration by parts with u being 2x and dv being e to the x dx, which makes du equals to 2dx and v equals to e to the x. So you have, you need to now apply the formula on the right again, which is uv minus v du. So uv 2x times e to the x, and you plug in 0, 4, and then minus v du, so e to the x times 2 times dx, so it's an integral of 2 e to the x dx from 0 to 4. Okay, so that's 17 e to the 4 minus 1. When you plug in 4, that's minus 8 e to the 4 minus, when you plug in 0, that's nothing. And then when you integrate 2 times e to the x, that's still 2 times e to the x, and you have to plug in 4 and 0. So, see, it's very confusing when you have all these signs. So maybe a better way to do it will be just to do the definite integral, indefinite integral first. So don't think about 0 to 4, and then simplify the result as much as possible, and only after that plug in your values. I think that's probably a better method. Or just use tabular. Tabular is much easier. Okay, so you have 8 e to the 4, and then when you plug this 2 e to the 4, that's a minus, but there's a minus here, so it must be 2 times e to the 4. When you plug in 0, it's minus 2, but it's negative of negative 2, and there's a negative again, so it's still just minus 2. and that gives me 11e to the 4, and then you have minus 3. So that's the final answer. And yeah, let me show you how to do the tabular. Well, I'm not going to explain how it works or what method that you have to do. I'll just show you what happens if you, assuming that you already know tabular, this is what you would do. You do plus minus d integral. You still use Lie to say x squared plus 1 is what you want to differentiate. E to the x is what you want to integrate. So differentiate, that's 2x, differentiate 2, and differentiate again. You hit 0. When you hit 0, you stop. E to the x integrates to e to the x, e to the x, and then this changes the signs. Then you go like this. Go like that. Go like that. And then the last row has to be multiplied and integrated, but since multiplying them you get 0, you don't get anything. Alright, so adding all of them, you end up with x squared plus 1 minus 2x plus 2 times e to the x as your final integral, and you're trying to plug in 4 and 0. Now, when you plug in 4 squared is 16, minus 8 would be 8, but then you add 3, so it's 11 e to the 4, and when you plug in 0, it's 3 times e to the 0, so it's minus 3. So you get this answer in a much quicker way. Alright, sine cubed of x. Now when you have a sine of an odd power of x or cosine of an odd power of x dx, then the way you solve this is by setting using the following things. Sine squared of x is 1 minus cosine squared of x, and for this one you would use cosine squared of x minus is equal to 1 minus sine squared of x. Hopefully you guys know this formula. Now if this power is even, that's a different story. If it's even, you have to use some other formula. I do have an example later which handles that case, so I'll explain that one later. Okay, so how do you use this? Well, first, rewrite this odd power as the product of an even power times the sine x. So if this was sine to the 5th power, then you would write sine squared times sine of x. So keep writing them as sine squared repeated, and then since this number is odd, at the end of the day you're going to have just one sine left out. Then what you do is you rewrite sine squared of x using this formula, as I said. Which naturally suggests that u should equal to cosine x, because if you differentiate cosine you get negative sine, so this is going to disappear. That's going to be like the artifact of the chain rule. Du is negative sine of x dx, so dx is negative 1 over sine of x du. Therefore this integral will be 1 minus u squared sine x dx is 1 over sine of x with a minus there du. And now you see that sine x disappears, and negative 1 times this will be negative 1 plus u squared, and that's perfect because now you only have u, and therefore you have successfully changed successfully completed the u substitution. Now integrate this, that's negative u plus 1/3 u cubed plus c. And when you do substitution, don't forget to go back. U was cosine x, so it's negative cosine of x plus 1/3 cosine cubed of x plus c. 2x cubed cosine x squared. This is somewhat strange because x squared is a nested function, so it looks like you need to do u equal to x squared. But then when you differentiate this, that becomes 2x, but this is 2x cubed. So what do? Well, if you have a nested function like this, you definitely need a u-substitution. So let's try to do the u-substitution, and let's see what we should do afterwards, okay? So we have u equals to x squared, and then du is equal to 2x times dx. And then we have dx equals to 1 over 2x times du. So when we have this is an integral of 2x cubed cosine of u, and then times 1 over 2x du, and 2 cancels. X cubed divided by x, what's that? X cubed divided by x is x squared, because this is x times x times x divided by x, so x is cancelled and you have x squared. So you have x squared cosine of u du, and this is not so satisfactory because you still have an x there. So we need to figure out what to do with this x. If I don't change this into some form of u, I cannot proceed. The u substitution is not complete, so I cannot proceed to the next step. Now, however, we are lucky because x squared, I see that it's equal to u, right? So I can just rewrite x squared as u cosine of u. Now, what if you're not so lucky? Well, in that case, what you need to do is you have to solve this for x, and then plug in square root of u into x, and then you simplify as much as you can. That would have worked in our case too, but there's some other cases where the relationship between the leftover x's and the new variable u is not so clear, and you have to actually solve for x. Okay, so now we have u times cosine of u. You no longer have a inside function. It says cosine of u. That means since it's a product, we need to use the integration by parts. And well, here's another problem. Since we used u already when we tried to do integration of u dv equals to uv minus v du, it's again annoying because you have to set u as something. For this case, somehow u is u, so that's easy. But you know, this formula is really like hard to use. I rather do tabular. So if you know your integration by parts, fine, go ahead and try to get the same result as I did. But for me, I'll just use tabular. Okay. So we have plus minus d integral u cosine of u differentiates to 1, 1 differentiates to 0, cosine of u integrates to sine of u integrates to negative cosine of u, plus minus plus, goes like that. So that's u sine u, and then sine u, and it goes like that. So that's plus cosine of u, and the last row has to be multiplied and integrated, but since it has 0, there's nothing there. And then you just have to put plus c because it's a definite integral. See how easy it is? Oh, and you shouldn't stop here because you set u equal to x squared, so the final answer should be x squared sine of x squared plus cosine of x squared plus c. Okay, log of x squared dx, that requires u equal to log of x. And then when you differentiate this would be du equals to 1 over x dx, so that dx is equal to x times du, which will make this into u squared x du. Again, we have an unsatisfactory case where you still have some x there. What do? You solve this for x. How do you solve this for x? Well, to get rid of ln, what you need to do is you raise both sides over e so that this cancels, so you have x equal to e to the u. So that gives you integration of u squared e to the u du, and I'll happily apply the tabular forgive me for doing this. Just if you only know integrate by parts, just carefully do integrate by parts twice. You have to do it twice, and then you're going to get the same answer as what I do here with much longer time. Okay, so that gives you this, which is u squared e to the u, negative 2u e to the u, and plus 2 times e to the u. The last run has to be multiplied and integrated, which is 0. So that doesn't give me anything. And then you put plus c, it's an indefinite integral. And since u is log of x, you do ln of x squared. And then instead of doing e to the ln of x, see that x is e to the u, so you just rewrite this as x. Okay, 2 times ln of x times x plus 2 times x plus c. So that's the answer. Okay, so here we have, oh, I forgot a dx here. You know, this is a very, very big mistake. I see students forgetting to put the dx all the time, and then especially it becomes a problem when you try to do u-substitution or integration by parts, because they rely on this. So make sure you never forget to put d of something. Okay, I'm sorry about this mistake. Let's try to do this. Well, since it's an addition, this time we can split this into 2 integrals. And this one, since you have a nested function, it suggests that I do 1 over x as u. So that's how you should calculate this first one. Whereas this one, well, it's a simple integration. You could do u equals to 2x, but that's an overkill. I know that negative cosine of x differentiates to sine of x. So if I differentiate negative cosine of 2x, I will get sine 2x. Well, almost, because there's a chain rule that you have to use when you differentiate this, and the derivative of this will create 2. So if you differentiate this, you're going to get 2 times sine of 2x. How do you get rid of this 2? Well, just divide by 2, and this will happily be that. So I know that the antiderivative of this would be negative 1/2 of cosine 2x. This way of calculating is much faster than doing u-substitution. Alright, since we have that one already figured out, let's just now focus on what to do on the first one. Since u is equal to 1 over x, du is equal to negative 1 over x squared dx. The derivative of 1 over x is negative 1 over x squared. You can either use the quotient rule or use the power rule by changing this as x to negative 1. Either way, this is what you get, and therefore dx is equal to negative x squared du. Let's see how everything works if I put that in there. Integral of e to the 1 over x. Well, e to the u. We did this hard work just so that I can rewrite e to the 1 over x as e to the u. So that's what we have. Let me erase this and write it again. Okay, so what I need is a u here over x cubed times, instead of dx, I have negative x squared du. And x squared and x cubed, they're reduced to x. There's still a minus. This minus is here. X squared over x cubed reduces to just x. And that's not good. This means that we haven't finished our u-substitution. So what do? How do we get rid of this x? Well, again, you want to solve this for x and plug it in there. Or you can just say this is like minus. You can pull the minus outside, right? But since this has x in there, you're not allowed to pull it outside. But you can certainly write it like this, and I know that 1 over x is u, so we can just rewrite it as negative u times e to the u du another perfect situation for a tabular integration. Plus minus d integral u10 either u, either u, either u, plus minus plus. So you have, let's see, I guess I'm ready to write down the answer now. Okay, so you have, remember this minus here, u times either u, it's like this, and then this is minus either u, and the last one has to be multiplied and integrated, that's nothing, plus we already have the integration for this one figured out, which is negative 1/2 cosine 2x, and then plus c. And you have to go back to your 1 over x here, so it will be negative 1 over x e to the 1 over x. Negative negative is positive. Positive e to the 1 over x minus 1/2 cosine 2x plus c. So this will be the final answer. Okay, now this one. This one requires integration by parts twice. And for this one, if you try to solve using tabular, it requires some knowledge. The knowledge is that for tabular, you have to stop at the third line. So when you have e to something and sine or cosine of something, tabular should stop at third line. Yeah, and actually this is why a lot of teachers do not teach the tabular integration, because you need to, while it's very fast, in some cases you have to memorize something extra. Okay, so I'll this time let me just do integrate by parts twice, so that if you are not comfortable with tabular, you can still follow me. Okay, so since Lee 8 says trig should be u and exponential should be the dv, in this integration of u dv equals to uv minus integration of v du, let's say u is sine of 2x minus 1 and dv is equal to e to 3x dx. If you differentiate u, you get du equals to cosine of 2x minus 1, and because of the chain rule, the inside function has to be taken outside and differentiated. If you differentiate 2x minus 1, you get 2, and let's put that 2 here. The antiderivative of e to 3x is 1 over 3 e to 3x, again because you're doing the opposite of the chain rule. You have to put this 1/3. And therefore this integral here is equal to uv is 1/3 e to 3x sine 2x minus 1, and then minus v du, so 1/3 times 2 is 2/3. And it's nice to put the 2/3 outside the integral because it's a constant multiple, e to 3x, and then you have cosine of 2x minus 1 dx. Okay, now we have u equals to cosine 2x minus 1. dv is e to 3x dx, whose derivative is 2 times sine of 2x minus 1, because derivative of cosine is negative sine, and the derivative of the inside function is 2. v is 1/3 of e to 3x, and you have to again write uv, which is these two multiplied, so 1/3 e to the 3x cosine 2x minus 1, and then minus v du, which is these two multiplied, and again you want to pull the negative 2/3 outside, and since there's a minus already, it'll be plus 2/3 integral of e to the 3x sine 2x minus 1. And what you notice is that you end up with the same integral you started with. At first it seems like this is just going around in circles, but actually something is indeed happening. If you put this integral as I, then what we found out is the following fact, that I is same as 1/3 e to the 3x sine of 2x minus 1 minus 2/3 times 1/3 is 2/9. 2/9 of e to the 3x cosine 2x minus 1. And then 2/3 times 2/3 is 4/9, and there's a minus, so it's minus 4/9 of this integral, but that integral is exactly the same as I, right? So I put an I there. Then what it's saying is that I is some kind of function that satisfies this equation. So you can think of this as an equation for I. So how do we solve it? We move this to the left, which is I plus 4/9 of I. And if I put the 1/9 outside, this is 3/9, so it's 3 times, well actually, e to the 3x is common too, so I'll pull the e to the 3x outside. So e to the 3x times 1/9 times 3 sine 2x minus 1 minus 2 cosine 2x minus 1 will be what we have. And let's just get rid of all the 9's by multiplying by 9. So it'll be 9 here, that's going to go away, that's also going to go away. So you end up having 9 plus 4, which is 13, and if you divide, the final answer is that you have 1/13 e to the 3x, and then 3 sine 2x minus 1 minus 2 cosine 2x minus 1, and then everything plus c. So that's the final answer.